The next phase in our analysis of WASP-12 is to go through and perform aperture and differential photometry. But before we do that, let's just quickly review where we are at this point. What we've done so far is to take the raw calibration files, create masters for them, and apply them to the raw science files. In addition, at the time we did that, we also created a new fits field for BJD TDB time. And the output of this process were a set of files called pipeline out files. So in this next phase, what we will be doing is taking those pipeline out files and first of all, determining the full width half maximum and seeing what AstroImageJ suggests for us for the aperture and annulus settings. We'll align images if necessary using a feature that AstroImageJ has called the Align Stack tool. We'll eliminate any bad images, select the appropriate comparison stars, and then be ready to begin the differential and aperture photometry. And in so doing, what we'll be doing with the aperture photometry is setting the aperture and annulus radii, setting certain information about our CCD, the gain, read, noise, dark current. These pieces of data are used by AstroImageJ to compute some of the error measures. We'll be setting limits for what our saturation is expected to be for the CCD camera we're using, as well as a linearity warning. We'll place the apertures on the target and comp stars. And as you will see, as we conduct the photometry, a measurements table will be created. So let's go ahead and load up the pipeline out files that represent our calibrated images. To do that, we'll go to the AstroImageJ main menu, select File, Import, Image Sequence. We will select the first file in the pipeline out directory. And when we hit Open, AstroImageJ will load up in its stack all of the images in that particular subdirectory. So let's go ahead and do that. And we'll go ahead and say, okay, there will be 336 images loaded up in the stack, as you see here. And again, we'll just sort of cycle through these images. We don't see any bad images. They don't appear to have much movement, so there's no need to align them. We'll cover that feature, by the way, a little bit later. So we're ready to now set some of the important parameters with respect to doing the aperture and differential photometry. As you recall, when we did an overview of AstroImageJ features, one of the features of AIJ was the ability to put our cursor over a star to see what the full width half maximum and the suggested annulus and aperture radii were for that measurement. So let's go ahead and do that. If you recall, we went to Analyze, but before we did that, we selected a particular star. Let's say this particular star, which in fact is our target, WASP-12. We'll just click on it. Then when we go to Analyze and Plot Seeing Profile, we see the profile of the ADU counts across different pixels beginning at the centroid of the star we've selected. And what you see here is the full width half maximum is 4.54 pixels. And what AstroImageJ is suggesting that we have an aperture radius of 9 pixels and that our annulus starts at pixel 16 through pixel 24. Now you've noticed, if you look at the worksheet, that what we used in the worksheet was an aperture radius beginning at pixel 13, inner annulus of 14, and an outer annulus of 29. Let's go ahead, though, for this exercise and use the suggested aperture and annulus settings that AIJ is suggesting, namely 9, 16, and 24. So the first thing we're going to do is to go into the multi-aperture photometry icon. We'll click on it here, and what comes up is the AIJ screen that allows us to do inputs of the various parameters that we'll be using for doing the differential photometry. We've already put in here 9, 16, and 24 for the aperture radius and the inner and outer radius of the annulus. We'll keep all the other defaults on this page, but it's important to go to the next tab, Aperture Settings, before we conduct the aperture photometry. On the Aperture Settings page, some important items to be filled in are the CCD gain. In our case, it's 0.3. The readout noise, again, in our case, it's 5, and dark current. Dark current for the camera used in this example is actually 0.003, but AIJ just sort of truncates it to 0. So we have very, very low dark current noise for the camera we're using here. We're also setting the saturation warning limit of 50,000 ADUs. This would indicate that we don't want our CCD for the target and COM stars to go beyond 50,000 ADUs, because we know that that is the saturation limit of our CCD detector. We're also setting a warning of 45,000 ADUs, just as sort of a flag that we're getting close to the overall saturation limit. So that's what these two options are. So for your particular CCD camera, you would set the gain, readout noise, dark current per the specifications of your CCD. And you would also set the saturation warnings and the linearity warning, again, according to the characteristics of your CCD camera. I would suggest keeping everything else as default, as you see here. And we'll now go back, and we're ready to place apertures on the target star, namely WASP-12, and on the comp stars. So let's go ahead and select Place Aperture. Now let's go ahead and put the aperture first on our target, and we'll select the target here, which is WASP-12. You notice that AIJ indicated it with T1, namely the target star of 1. And the count here that you see, the 4.994 times 10 to the 5th, is in fact the integrated counts that you also see up in this box. So when we put our aperture and annulus here, you see that roughly that's the same counts that you see up here. Next, let's select a comp star below the target. Let's select this as C2. Let's select this star as C3, this one as C4, and this one as C5. By the way, as you're doing these selections, you'll notice that you don't have to put your cursor exactly over the star. Pretty close enough, however, because AstroImageJ will go ahead and find the centroid of the star and select it automatically for you. So we've selected a target star, WASP-12, and we've selected 4 comparison stars. So now we're ready to conduct the photometry for all of the 336 images that are in the stack. When we hit the enter bar, or the enter key, what will happen is AstroImageJ will go through each image, will compute the ADU counts in the aperture, in the annulus. It will determine what the ADU counts are for the central aperture after the sky annulus is taken out of the equation. And it will do that for all of the stars, the target star and the comp stars. And in so doing, it will be creating a measurement table. And let's go ahead and now hit enter, and AIJ will cycle through all of the 336 images as you see here. And in the background, it's constructing a measurement table. We will pick up here in a moment when this process is completed. Okay, so AIJ has now completed going through all of the 336 images and has created the all-important measurements table. So let's take a look at this table. And what we see first of all is that there's a row for each of the 336 images, and the columns going across contain the name of the file, name of the image file, the slice number in AIJ stack, an indication whether there was any saturation that occurred of the target or comp stars, the various time bases, and in particular, the BJD TDB times, the air mass, the exposure time. It records for us the aperture and annulus pixel counts as far as the pixels that we set those radii for. And the most important numbers are the relative flux counts for the target and each of the comp stars. Now, the way AstroImageJ computes relative flux is it first computes for each of these stars, the target and the comp stars, the source minus sky counts. So for T1, what this represents is it takes the ADU counts in the aperture and compensates for the background sky contribution that is determined from the annulus. I won't go through the formula for doing it, but effectively, this number represents the ADU counts for the target after the sky background is taken out. The same takes place, the same computation takes place for each of the comp stars. And as you see here, for example, source minus sky of C2. So let's go back to the relative fluxes, which again are really the key numbers out of this table. So the relative flux of T1 is the net counts, ADU counts, that is the source minus sky ADU counts for T1 over the sum of the source minus sky counts for all of the comp stars. Basically what it's saying is that relative flux of T1 here is a measure of the net counts for T1 relative to all of the comp star counts. The relative flux of each of the comp stars, however, is the relative flux of comp star C2, for example, over all of the other comp stars. The target source minus sky counts are not included in the denominator for these relative flux numbers for the comp stars. So these counts are relative to the comp stars. This count for the target is relative to all of the comp stars, but of course not itself. So that way we can then look at comp star 2 later, for example, relative to the other comp stars to see if in fact it is varying, which it theoretically should not be. You also see in the measurement table here other information having to do with the relative flux errors, signal to noise ratios, and so on. But the important numbers, again, are the relative flux numbers. Now, in addition, if one wanted to see what the variation is of the images across the CCD detector, if you take a look at both coordinate systems, either the ImageJ coordinate systems is indicated here, X and Y, or the FITS coordinate system, as you see here, you'll see that in this example there's very little variation. So that says that from image to image, these images stayed on pixel 336, 337 in the X direction, and 504 as the Y coordinate for that pixel. So very little pixel to pixel movement. Okay, so that's an overview of the measurement table. I would say it's always a good thing to save the measurement table, and let's save that in the AIJ analysis subdirectory. So we'll go ahead and save it there. So this completes the aperture and differential photometry phase. We've created the measurements table, and now we're ready in the next phase to start doing the transit modeling, fit, and optimization. I should point out that there's a number of other variants to what we just went through. I would suggest reading through the guide that I've indicated before, can be obtained at astrodentist.com. Some of the other variants to this process would be if the images are not correctly aligned, how they can be aligned using various AstroImageJ facilities for doing it. In addition, there is the provision for taking care of a meridian flip, in which case the images are actually transposed across the diagonal after a meridian flip takes place. So it's important to review those parts of the guide just to understand some of the other variants that need to take place during the differential photometry process. So that concludes this phase, and in the next phase, as I said, we'll get ready to do the actual transit modeling.